Today we are going to discuss about the Motional EMF. What is Motional EMF? When a conductor of length L moves in a uniform magnetic field which is placed perpendicular to the conductor and the conductor moves perpendicular to its length, then across the two ends of the conductor, an EMF is induced. That EMF is called Motional EMF. When a conductor of length L is moved with uniform velocity V in a perpendicular magnetic field, and the conductor moves perpendicular to its length, then an EMF is induced across the two ends of the conductor, and that EMF is called the Motional EMF. That means that so this is the magnetic field. Cross means perpendicularly inward magnetic field. If a conductor moves like this, perpendicular to its length, then across the two ends of the conductor an EMF is induced. An expression of induced EMF is BLV. B is the magnetic field induction, L is the length of the conductor, and V is the velocity with which the conductor is moving. And this EMF is called Motional EMF. But if the rod moves like this, if the rod moves parallel to its length, then no EMF is induced here. If the rod moves parallel to its length, no EMF is induced. Now we want to derive an expression of Motional EMF. So this is a rectangular frame. This is the inward magnetic field. This is a rectangular frame, and resistance of this wire is negligibly zero. Resistance of this frame is negligibly zero. Now I place a metallic conductor PQ. Here. This is the P, this is Q. I place a metallic conductor PQ, and this conductor moves in this direction with velocity V. Let the length of the conductor is L, and this distance is equal to X. When this conductor moves in this direction, effective area of this loop decreases. So as a result, inward magnetic flux linked with this area. Why inward? Because magnetic field is perpendicularly inward. Why perpendicularly inward? Because magnetic field is represented by putting a cross. So when this conductor moves towards the left with velocity V, area of this rectangular loop decreases. As a result, inward magnetic flux linked with this loop decreases. Inward magnetic flux decreases means an EMF is induced, and due to that induced EMF a current flows, and the induced current obeys the Lenz's law. That means it opposes the basic cause which produces it. So what is the basic cause? Decreasing magnetic flux, decreasing inward magnetic flux. Therefore, a induced current flows in the circuit like this. We may remember in this way also, when the conductor moves in this direction, inward magnetic flux decreases. Inward magnetic flux decreases means north pole is moving away. So therefore, a clockwise current flows in the circuit. If it clockwise, it produces south pole. There is an attraction between north and south pole. So it obeys the Lenz's law. Is it clear? This length is x, this is L. So what is area of the loop? L into x. So what is magnetic flux? Magnetic flux linked with this particular loop at any instant is BLX. So what is d phi by dt? Because if this conductor moves in this direction, effective area decreases. Why? Because x decreases. So therefore d phi by dt is BL dx by dt. That means if this conductor moves in this direction, this length decreases. This length decreases. That means x decreases. This length decreases means x decreases. So BL dx by dt. Here dx by dt is equal to minus v. Why minus v? Because when this conductor moves in this direction, effective area decreases. So therefore minus v. So therefore d phi by dt is equal to BL minus v. From here we get minus BLV. According to Lenz's law, according to Lenz's and Faraday's law, d minus d phi by dt is curl of E. Therefore minus curl of E is equal to BLV. Therefore E is equal to BLV. So this is the expression of Motional EMF. Instead of applying the direction of current like this, we may use the Fleming's right hand rule also. What is the right hand rule? Fleming's right hand rule? Right hand, not the left hand. Fleming's right hand rule. This is the four-finger field. This is central finger, direction of induced current, and this is thumb. Thumb means the motion of the conductor. Motion of the conductor. So here I have to hold my hands in this direction. I have to hold my hands in this direction. Four-finger field perpendicularly inward. This is the motion of the conductor. This is the motion of the conductor. So this is the thumb. So therefore this is the direction of induced current. That means in this conductor, direction of induced current is in this direction. That means from P to Q. It is from P to Q, it will move like this. P, Q, R, S. The current flows in this direction. That means across the two ends of the conductor an EMF is developed. And what is the polarity of the EMF? Polarity of the EMF is this. Potential of the point P is negative. Potential of the point P is negative and potential of the point Q is positive. That means it behaves like a battery. It behaves like a battery and polarity of the point P is negative and polarity of the point Q is positive. Because we know that inside the battery current flows from negative terminal to positive terminal. Is it clear? That means what is motional EMF? When a conductor moves in a perpendicular magnetic field in a direction perpendicular to its length across the two ends of the conductor, an EMF is developed and that EMF is called motional EMF. Now we want to discuss about the energy consideration in motional EMF. Energy consideration in the motional EMF. Let us assume that resistance of this particular part is negligibly zero. That means QRSP, this part is practically zero. And resistance of this conductor PQ is capital R. So therefore, what is the current? What is the current through the conductor PQ? What is the current through the conductor PQ? The current through the conductor PQ is EMF divided by resistance. So it is BLV by R. So this is the current through the conductor PQ. Now you returns back to magnetic Lorentz force. When this conductor moves in this direction, we may assume that a current carrying conductor is inside the magnetic field. A current carrying conductor is inside the magnetic field. Now, according to Fleming's left-hand rule, what is the direction of magnetic Lorentz force? What is the direction of magnetic Lorentz force? This is the Fleming's left-hand rule. Forefinger field, central finger current, thumb gives us the direction of magnetic Lorentz force. Magnetic Lorentz force. That means when we try to move this conductor in this direction, magnetic field exerts a force on the conductor in this direction. When we try to move the conductor in this direction, magnetic field exerts a force on the conductor PQ. Magnetic field exerts a force on the conductor PQ in this direction. That means opposite to the direction of motion of the conductor. What is that force? It is BIL sin 90. Why sin 90? Magnetic field is perpendicularly inward. So this is the direction of magnetic field. This is the direction of current. So this angle is 90 degrees. So BL sin 90. What is I? I is BL V by R. So magnetic field exerts a force on the conductor which is B square L square V by R. And direction of the force is towards the right. According to Fleming's left-hand rule, the direction of the force is opposite to the direction of motion of the conductor. Therefore, this is the right. Therefore, what is power required to push the conductor in this direction? Why the power required? Why we have to do the conductor? Why we have to do work to move the conductor? Because when this conductor move in this direction, external agent has to do work against this opposing force. So therefore, power required to push the conductor. What is power required? Power means force into velocity. Force into velocity. In HS first year, we got this relation. So it is B square L square V square by R. That means when we try to move the conductor inside the inward magnetic field, a induced current flows through the conductor from P to Q, and because of that, magnetic field exerts a force on the conductor which is towards the right. And what is the magnitude of the force? Magnitude of the force is BIL. What is I? What is I? I means the induced current. What is I? I is equal to BVL by R. BVL by R. So therefore, this is the force. So in order to move the conductor, work has to be done. So what is power of that work done? Force into velocity. We are getting this. We know that according to conservation of energy, energy cannot be created nor be destroyed. So in this case, in order to move the conductor, work is done. That means some energy is given to this system. Where that energy goes? This work done, the energy gained by the system during the work done to move the conductor is dissipated as heat energy, is lost as a heat energy that produced by the induced current. So what is the heat loss? What is the power of heat loss? Or what is the rate at which heat is produced in the conductor? The rate of heat energy produced in the conductor due to the induced current is equal to I square R. What is I? Induced current, magnitude of induced current. What is R? Resistance of this conductor. Therefore, rate of heat energy produced in the conductor PQ is equal to this. So I squaring it, I will get this. Okay? So rate at which heat energy is produced in the conductor PQ due to induced current is this. So if you see the expression 1 and 2, they are similar to each other. They are similar to each other. That means that the mechanical power delivered by external agent to move the conductor PQ is dissipated as heat energy in the conductor PQ. Mechanical power delivered by external current to move the conductor PQ is dissipated as heat energy in the conductor PQ. Okay?